We're going to start the second video on intermolecular forces by focusing on hydrogen bonding. And here you can see that I have a number of molecules of water. Water is H2O. You can see very clearly the covalent bonds. Covalent bonds exist between nonmetals and nonmetals, in this case hydrogen and oxygen. I've drawn the water molecules as being bent in shape, and I've shown the two electron pairs that are not bonded, the two lone pairs. So hydrogen has four electron pairs on its central oxygen. I think I said that wrong. Water has four electron pairs on the central oxygen atom. Two are bonded pairs and two are lone pairs. So if we're talking about bonds, these are bonds, covalent bonds. But our topic now is intermolecular forces of attraction. A hydrogen bond exists when a highly electronegative element, such as oxygen, is attracted to the hydrogen of a second molecule. So you can see how if this hydrogen has its electron pull towards the oxygen, making the oxygen more electronegative, all that's left here for this hydrogen is a proton in the nucleus. This positively charged proton, the positive end of the molecule, is attracted to this lone pair on a second molecule. So we have hydrogen bonds setting up. And because of the shape, because it is a tetrahedral electron pair geometry, but a bent shape, these hydrogen bonds set up in many different directions. Now, the amazing thing is that what I'm showing you here is what happens in a cup of water. This is our cup of water with lots of water molecules in it. And all of the electron pairs of one water molecule is attracted to the highly electronegative lone pairs on an oxygen. And you can see that what happens is that it sets up this pocket of space here. And in this space, this is what happens when water freezes. When water freezes, these hydrogen bonds are made. As water goes into the solid state and the particles are closer together, these hydrogen bonds are going to be formed. And as these hydrogen bonds are formed, they're rigid. So the molecules take on a certain shape. Now, what happens if you start to take ice, water, in the solid phase, and you start to heat it up? Well, the heat is going to be used to break bonds. What do I think is going to break first? The weak intermolecular forces of attraction, worth maybe 2 to 4 times as much in energy as the covalent bonds? Of course, the hydrogen bonds are going to be the first thing to break. And imagine what happens with my image here if all of the hydrogen bonds start to break due to the addition of energy. What's going to happen is that this space is going to collapse. And the particles of water, the molecules of water, are going to come closer together. What does this tell you? Well, this tells you about something that's different between ice, where the pockets are there, and water liquid, where the pockets collapse. What you know is that ice floats. Very unusual. If I were to have asked you which is more dense, the solid or the liquid, we think of solids as being more dense. So the solids should go to the bottom if you have a mixture. The more dense material will go settle to the bottom. Rocks settle to the bottom of a lake. But when you're talking about ice, and you think about dropping a solid block of ice into a glass of water, the solid doesn't sink to the bottom. The solid floats. There are only about 4 substances that are common that might do this, and we're very thankful that they do. Because, like now in the wintertime, if our lakes were to freeze from the bottom up, that would be disastrous. All the plants and animals in the lake would die, and they'd be caught in an ice cube. Our lakes freeze from the top. There's going to be a surface film of ice, which kind of protects the plants and the animals from additional cold. So ice floating is very unusual, and this is one of the properties of water that we want to be able to understand and explain. The second property of water that we're very interested in is going to be related to what happens with boiling points. Let me see if I can straighten this up now. And so I'm going to take substances, and I'm going to start with hydrogen. And I'm going to talk to you about, well, I could talk about melting points, but I think you'll be more familiar with boiling points. And so if I look at hydrogen's boiling point, hydrogen is going to boil at negative 253 degrees Celsius. This is all going to be in degrees Celsius. Now, what does that mean? It means that if I have two hydrogen molecules, we'll just use these 2 pens as an example. If I have these 2 hydrogen molecules, if they were ideal gases, there are no forces of attraction and repulsion between them. But we know that very few gases behave ideally. And so, when we consider the intermolecular forces of attraction that are there, the weak London dispersion forces bring these molecules of water, hydrogen, slightly closer together, but they're still going to be in the gas phase. Now, what if we were to look at something that was a little bit larger? Something like oxygen. Well, two oxygen molecules with no forces of attraction would be in the gas phase, but there are forces of attraction, and these forces of attraction are going to bring them closer together. The only force of attraction that they have is the London dispersion interaction. All molecules have this, but O2 is larger than H2. So while H2 might bring the particles slightly closer together, because oxygen is larger and has a larger London force, it's going to bring the particles closer together still. Still in the gas phase, and the boiling point for oxygen is negative 183 degrees Celsius. What if we were to look at something like methane, CH4? Now, we've got a lot to consider here. It may not have as much mass as oxygen. Oxygen is 32 grams per mole. Methane is only going to be 12 plus 4, 16 grams per mole. So by mass, oxygen is larger, but if you think of methane, methane is tetrahedrally oriented. Bond angles of about 109. It's going to take up a lot of space. So it's not just mass that we must consider, it is also volume of the particles, the volume that they will occupy. Methane has a boiling point of a negative 164 degrees Celsius. So, even though it's much smaller in mass, it has a substantial London force. And then after methane, what if we were to take something like this, carbon tetrachloride? Woo! Still tetrahedrally oriented. Around the carbon atom, we find our 4 chlorines. But these 4 chlorines are huge and massive. And so carbon tetrachloride is going to have not only volume, but lots of mass. And its boiling point is going to be 77 degrees Celsius. Do you understand what this means? Carbon tetrachloride boils at 77 degrees Celsius. Carbon tetrachloride is a liquid. Under standard conditions, room temperature is about 20 degrees, we would actually have to heat this up to get it to go into a gas phase. And then after carbon tetrachloride, we should look at one more molecule. And this molecule is going to be benzene. I'm not sure how much we've talked about benzene, so I'm going to draw its structure over here. Benzene is a ring of 6 carbons. There's my 6-carbon ring. And you know that carbon makes 4 bonds. So what we have here is alternating double bonds. Now we see that each carbon has 3 bonds, so every carbon would have 1 hydrogen attached. Now, for those of you who remember, what we are going to experience in benzene molecules is that I had a choice in where to place the double bonds. So this is going to resonate. And so in benzene, there really are no single or double bonds. Instead, we would show this carbon structure. Here's our 6 carbons again. And the second bond is going to be shared around the structure. So, because of it being this large open ring structure, C6H6 benzene is going to occupy an extremely large volume compared to the other substances that we've examined here. And benzene is going to have a boiling point of about 80 degrees Celsius. So it may not have the mass, but it has volume. So London forces are going to be determined not just by mass, but also by volume. And this helps us to see something, because now, if we look at all of these substances, they are all similar. They are all nonmetals to nonmetals. These are all nonpolar, covalent molecules. All of them. They're all nonpolar. There's nothing here that would impart any polarity. So I want to show you one more molecule that will compare to these, maybe even 2. Let's look now at ammonia, which is NH3. Let's just look at the fact that it has a boiling point of negative 33. Ammonia is already going to be a volatile gas. And let's look here at what we have with ammonia. With ammonia, and we can compare it to the methane up above. Methane, CH4, has only London forces pulling it together. Pretty substantial, but still methane, which comes from our gas jets in the lab, are gases. Ammonia is going to have not only a very similar London force, because the sizes are similar and the shapes are similar, both about 15, 16 grams per mole, both based off tetrahedral electron pair geometry. So their London forces are going to be similar, but ammonia has nitrogen. And this nitrogen is going to make it polar because of its shape. Think of what you learned in Vesper. So there's going to be a dipole, pulling it closer together, a dipole-dipole bond, or interaction, sorry. And then because FON is going to hydrogen bond, this ammonia is also going to have hydrogen bonding, which will pull 2 ammonia molecules close enough together to be in the liquid phase fairly easily. So while ammonia has a boiling point of minus 33, and we think of ammonia as a gas, it can be easily liquefied. We'll look at one more molecule, which is OH2. I'm writing it backwards so that we can focus on the central atom, which is oxygen. And here, water, similar in mass, will have a London force. It will have a dipole because nitrogen and oxygen are both polar, but because of the extensive hydrogen bonding, water is found as a liquid. And you know that the boiling point of water is actually 100 degrees Celsius. Why? Because of all the different forces of attraction pulling the two molecules together into the liquid phase, we're going to have to use more energy, more heat, to get them to go back into the gas phase by boiling.